We will basically be talking about generative adversarial networks. We will see the theoretical parts of the GANs, and we will do a hands-on example. So you will understand how GANs work, what basically they do, and then how you can train them and how you can basically use them. We will use the ideas behind convolutional neural networks. It's not that different, but it's slightly more difficult. We will see some different terms. We will have different layers. And with the convolutional neural networks, what we have seen up until now is a sequential model. So we start with something, we basically train it, and then we use it. In the generative networks, we have a slightly different architecture. So we will first see what we can use GANs for. It's the GAN Intuition part, and then we will see how we can train a GAN. And then we will see some examples. Then we will have a hands-on example with Tensorflow, how we can basically use Tensorflow to train a GAN. Okay. So what are generative networks? With the deep convolutional neural networks, the problem we solve is we give the picture of money, right? And then the deep convolutional neural network says whether that's a money or not. That used to be the problem we were trying to solve up until now. So we have a deep convolutional neural network. We give a picture, and then this network says whether this is a picture or not. That was the very basic idea behind the deep convolutional neural networks. With the GANs, the problem is a little bit different. Now we have some random numbers, and we give these random numbers to a reverse deep convolutional network, which is the generator network. And the output is basically the picture of money. So the problem is basically the other way around. In the convolutional neural networks, we give the picture of a money, ask the convolutional neural network whether this is a money or not, and it says whether that's true or false. With the GANs, the problem is the other way around. We basically give random numbers to our generator network, and the output of the network is basically the picture of money. Okay, that's basically the very, very basic intuition behind the GANs. So how do we use GANs? We can use it for text-to-image translation. That's what we basically do with this Leonardo AI or Lexicart or Midjourney. You define an image with text, and the generative network basically translates this into image domain and creates you an image. That's the same idea behind ChatGPT as well. These are generative models as well. You can do basic image editing, image manipulation with GANs. You can create images 2-dimensionals or 3-dimensionals, or you can recreate images of higher resolution. That's basically called super resolution. So let's see some examples of GANs in order to understand it in a better way. Let's say we are given some images, and let's assume that we have some magical structure, magical black box that can convert our given images into some art master's style. For example, you give this image, you get an image that looks like it was created by Monet or Van Gogh. Okay, that's basically what GANs do. They basically forge stuff. They create stuff. So you give this picture of Amsterdam, basically creates you a painting of Van Gogh from your picture, or a painting of Monet from your picture. It's the same with this example. You give the image of a horse, it creates you a zebra, or the other way around. You give zebra, it creates you horses. You give the photo, it creates you a painting of Monet, or the other way around. You give the painting of Monet, it creates you a photo. It's basically forging stuff from what it learns. You give the image of summertime, it creates you a wintertime image, or the other way around. You give a wintertime image, it creates you a summertime image from that. And it's basically being used a lot for style transfer, meaning you have basically the style of a master painter. You basically just give a photograph, an image, and then it creates you this painting like images. And that's yet another important implementation of GANs. You are given a historical, nostalgical photo, and like in the movie Harry Potter, it's basically making your photo alive with expressions, facial expressions, or other stuff. So how it works? Basically, assume you would like to forge this painting from Da Vinci. Okay, we have a lot of paintings from Da Vinci, and we study Da Vinci. We know how he draws. We studied him a lot, and we would like to forge this particular painting. And we studied Da Vinci a lot, his technique, and we basically learned how to draw like the original painting. And we painted a lot. I mean, we tried a lot, and then we came up with something like this. So this is how we studied. We studied every move of Da Vinci. We studied every style of Da Vinci, and we came up with something like this. So this is how we forged the image. Now assume there is yet another master painter who is not Da Vinci, basically another master painter that can evaluate our paintings, and he can basically says whether our forged paintings are good or bad, whether it looks like a painting from Da Vinci or that's not a good forge. This master painter can say this. So that's how basically GANs work. We have two networks working together. We have a generator network, which is forging the image. So this was producing the Mona Lisa image. And we have another network that's working at the same time, which is discriminator network, that's saying whether the forged image is good or bad. Okay? And the basic idea is you feed the generator with random noise. That's the same with the fake money or forged money example at the very beginning of the lecture. You basically feed the generator with random noise. And then the generator generates you a fake image. And then we have another network, discriminator network, which basically sees both real samples and fake samples. And it can say whether something is real or forged. That's the job of the discriminator. So the job of the generator is generating images, and the job of discriminator is basically discriminating whether something is forged or it is genuine. Okay. So GANs are the most interesting idea in the last 10 years in machine learning. Yann LeCun says that's one famous guy for machine learning. GANs were developed by Ian Goodfellow in 2014, and GANs are formed of two competing networks known as the generator and discriminator. And bringing these two networks together, we let them fight. You can think the generator as a forger or as a thief, and you can think the discriminator as a police that's trying to stop the generator. And the job of generator is producing fake images, for example, generating fake money, and the job of discriminator is trying to discriminate between fake and real images. Okay, you just need to remember we have two competing networks. One is generating, the other one is trying to discriminate whether the generated stuff is forced or real. Okay, this is basically the whole idea behind GANs. And these networks grow together. I mean, we train them together. It's not like you train a discriminator. Once you have a perfect discriminator, you train a generator. That's not how it works. You basically train these two networks together. We will see while we are doing the example how we can train basically a GAN. It's not as easy as training a convolutional neural network. It's a bit more complicated. We will need more operators, but what you need to remember is these competing two networks in GANs, they grow together. You train them together. It's not like you train discriminator first and generator afterwards. You train them at the same time. So how you basically make things work? The generator never sees real money. Let's talk about money. Okay. We have real money and we have fake money in our system. And the generator never sees a real money. But the discriminator sees both real money and fake money generated by the generator. So this is one thing you should remember as well. Discriminator needs to see real money because he's gonna discriminate between real money and fake money. If he doesn't know how real money looks like, he cannot distinguish between fake money and real money. Okay, and both discriminator and generator are trained. So generator learns generating money, discriminator learns what real money looks like, and in each iteration, generator tries to generate much better fake money, and discriminator tries to learn discriminating fake money and real money in a better way. So that's why these two competing networks, the generator and discriminator, they grow together. So GANs work by having a generator network that's you can think as a counterfeiter who's being trained to create fake dollars that are indistinguishable from the real ones generated by the bank. And the discriminator network, the police, is being trained to determine if the money is real or fake. So over time, the generator will become expert in generating new money that are indistinguishable from the real ones, and the discriminator will fail to tell the difference because it's gonna be almost perfect. So the discriminator will not be able to tell the money is real or fake. But at the beginning, as we will see in the example, the generator will generate crap. It's really gonna be crap because it's being fed by random noise. It's gonna convert random noise into something, and in the first iteration, it's not gonna look like anything. And the discriminator will obviously say, okay, this is the real money, this is the fake money, this doesn't look like real money, and it's gonna say, okay, you need to make it better. And in the second iteration, the generator will try to make better money, and discriminator will try to learn to distinguish it in a better way. So GANs are capable of generating new images that have never existed before. As you have seen in Midjourney and Leonardo AI examples, you can basically generate text or generate images, generate videos, generate 3D stuff. So the whole thing behind all this technology is the GANs, basically. And GANs learn about the features of objects and create their own images or own structures or own text. GANs consist of a generator and discriminator network. Both the generator and discriminator start from scratch and they learn together. So it's not like the generator basically knows something about the problem. It doesn't. You define the architecture as we did in the convolutional neural networks, and then we train this architecture together, both the discriminator and the generator architectures. The generator will generate images, and the discriminator will compare these newly generated images to the true images that are contained within the training set. Okay. And the generator works by trying to fool the discriminator by convincing it that the newly generated images are real ones. Both networks learn together until the generator becomes a master at generating brand new images that are indistinguishable from the real ones, or until it converges. So the generator takes in random noise and output images. So it really gets just random noise. It's just random noise and it's outputting an image or it's outputting a text. And the discriminator is a basic neural network that's trained to perform classification tasks. So the discriminator is nothing but a convolutional neural network with a little bit difference. In the training phase, it's slightly different than a usual convolutional neural network. And as you will be seeing, we have some additional layers for the discriminator and generator. So the basic architecture for a GAN is we have random noise here, we have the generator. The generator is producing fake money or fake images. This is fed to the discriminator. We are feeding real money to the discriminator as well. Therefore, he basically knows what real money looks like, and he basically knows what fake money looks like. And in the end, during the training phase, what he does is he basically adjusts its weights and biases so that it can distinguish real money and fake money in a better way. And then it gives basically some feedback to the generator so that the generator can basically generate much better fake money. So how do we train a GAN? So we said they need to grow together. I mean, you cannot just train one part of the GAN and then leave the rest. You need to train them together. So how do we train the discriminator? So this is gonna be in parallel, but let's first see how we basically train the discriminator. So discriminator needs to see real images as well as fake images, or it needs to see real money as well as fake money, so that he knows what real money looks like and he knows what fake money looks like. And during the training phase, basically gets images from the generator, the fake images, and it gets real images from our training set, and then it adjusts or updates its weights with respect to the loss both from fake images and real images. So this is one thing you need to remember. The discriminator's weights are updated by using the loss from real images as well as fake images. That's not true for the generator. The generator's weights are updated by just using the feedback from the loss of fake images. So the discriminator training is performed as follows. The generator will take in random noise and generate fake images. That's the first thing. The generator needs to generate fake images. Both fake images and real ones are fed to the discriminator network. You need to do this at the same time because you need to basically calculate loss for both fake images, for fake money and real money. Okay. The discriminator will generate predictions based on the input images, both for real and fake. Discriminator predictions are then compared to the true labels to calculate the error or the loss. Okay. And the problem is a basic binary classification. The discriminator is trying to predict 1 for real images and 0 for fake images. And the error is propagated through the network to update the discriminator weights. That's the big propagation phase. So you calculate loss from fake images or fake money and real images or real money. You basically calculate the loss and then you update the weights of the discriminator. The generator weights are not updated at this stage. So we will be updating it right after this. So once we freeze the weights of the discriminator, we will be updating the weights of the generator. So we have the same image, we have the fake money. Our objective was to basically trick the discriminator and pretend as if it is a genuine real image. And the discriminator is gonna say whether this is fake or not. And depending on its decision, we will be calculating some loss. And the generator will be benefiting from the loss of the fake money. It's not gonna be using the loss from the real money. Okay. So the generator training is performed as follows. The generator will generate fake images. That's the same loop with the discriminator. The fake images are fed to the discriminator and it will generate predictions or the probabilities. The discriminator output will be compared to ones because it's trying to fool the discriminator to think that this is a real image. And then the generator weights are updated while the discriminator weights are frozen. That's one important aspect as well. Two things to remember. The discriminator weights are updated from the loss of fake images as well as the real images. The generator weights are just being updated from the loss of fake images or fake money. So these are the things you should remember. You will be seeing how that's gonna work with the hands-on example. I know it's not that easy to understand how they basically compete with each other, how they work together. But once you see the example, it's gonna be more clear. Both the generator and discriminator are working against each other to get better at their assigned task. At the same time, they share information by assisting each other as well. The generator shares the forced images and the discriminator shares the loss of these fake images. And after multiple epochs, the generator becomes expert in generating real images that are indistinguishable from real ones. And the discriminator will reach a state when it cannot distinguish the real from fake images. Okay, that's basically how you define a GAN, and that's basically the idea behind GANs. Now let's first see some real-life examples of GANs where we use basically GANs, and then we will work on the hands-on example. So this is one application. I know these are not too interesting anymore because you basically see much better stuff with Midjourney or Leonardo AI or other generative networks, but you can basically generate cartoon characters with GANs. That's one application. Pose-guided person image generation. You basically have one image. From that image, you can change the pose with GANs. You can have a model with just one pose, and then from that pose, you can generate other poses. That's one thing you can both use for fashion world as well as for training other networks. So GANs are usually used to generate data to train other networks. Let's say we're gonna solve the problem of finding persons, for example. And in order to generate a lot of data with different poses, it's a good idea to use GANs. So we can basically generate faces, we can change the expressions of faces, we can change the hair type, gender, we can age faces, we can change the color, skin color, for example, we can make it more pale, we can make it more dark, we can add expressions. For example, this is the input image, we can make that person angry, we can make it happy, we can make it fearful. You see other examples as well. So GANs are pretty good at forging faces. If you, for example, take a look at DID, you will see it's using faces for movie generation. Google and other companies right now have a lot of studies and research on generating general videos, but they're not released yet. Most of the things we can use concerning video generation is about faces right now. So we can basically use GANs for suggesting merchandise based on celebrity pictures. You can basically have your clothes, you can put that cloth on a person by using GANs. That's yet another application of GANs. Or you can basically get the image of a person and then you can get which merchandise is closer to what you see on the image. That's another application of GANs. You can use GANs for super resolution or increasing the resolution of an image. This is basically an increased resolution by bicubic interpolation. That doesn't look so good. That's a lot blurrier than the other ones. And these are examples from some super resolution algorithms. And this is the original image. As you see, it's quite difficult to distinguish between the GAN generated images and the original one. We can basically use GANs to synthesize photorealistic images for segmentation problems. That's one application of GANs as well. We can use GANs for image inpainting. That's the problem of filling gaps with images. So it's usually not that obvious. I mean, if some part of your image is missing, like these ones, so these are on purpose cropped parts of the image, you can use GANs in order to fill that parts of the images. That problem is called the image inpainting. And as you see, since the GAN knows the domain the image is coming from, it's basically filling it with content. If you were to use low-level image processing, you would just use the brightness values closer to this part, the missing part, and if the missing part is too big, as in this example, it's really difficult to fill it with basic image processing techniques because you need to know the contents. I mean, you need to know this is the image of a dog, and if the dog would be full, I would fill these empty parts with this. Okay, so the image inpainting is carried to another level with GANs. Super resolution and image inpainting is most basic and most successful applications of GANs when it comes to image processing, apart from image generation. So you can basically generate styles. You are given an input handbag, for example, and the output is if you wear this shoe, for example, with this handbag, then you have a good style. So it's basically producing you a matching style for fashion purposes. And yet another example of GANs is music generation. You basically train your network and then it starts generating you new melodies. Music generation is yet another example for GAN usage. So before we dive into the hands-on parts of the lecture, we will see a concept called batch normalization. So batch normalization is an algorithmic method which makes the training of deep neural networks faster and more stable. So it consists of normalizing activation vectors from hidden layers using the first and the second statistical moments of current batch. And this normalization step is applied right before or right after the nonlinear function, which is basically ReLU. As you see in this code, you create a layer and this is the nonlinear parts, the activation function, and in between you apply this batch normalization operation. And in practice we consider the batch normalization as a standard layer such as a perceptron, a convolutional layer, and activation function or a dropout layer. And Usually batch normalization is positioned right before the nonlinear function, which was consistent with the authors of object design hypothesis at that time. So we will be using batch normalization as a new layer. We will see this new layer as leaky ReLU with the GAN example. So these are two new things that we will be using. All right, now let's take a look at our hands-on example for the GANs. It's a bit lengthy. It's slightly more difficult than convolutional neural networks. We will be using MNIST database, the handwritten digits. We will be forging handwritten digits with this example. So the aim of this example is to create a generative network. We will basically provide random noise, and then our generator will produce handwritten digits for us. So that's basically the idea. As usual, we basically import the required libraries. This time we will be importing TensorFlow Keras layers as well. This is an old function I provided you, taken from Towards Data Science, in order to load the MNIST database. You should have the MNIST database train images in your data folder. I will be providing them again in the description of the YouTube video. Now we will just be loading the training and test images, as well as training labels, as well as the test labels. And then we need to convert these guys into 28 by 28 images, or 28 by 28 tensors. If you remember, the MNIST database was basically storing them as a vector, one-dimensional vector. So we need to convert them to tensors. And with this operation, we convert them to tensors. Now we have some definitions. We will come back them to later, but for now, we have a batch size of 256. So the batch size will be used to tell the network you are not going to use all 60,000 images at the same time for training. For each training epoch, you will iteratively use 256 images. So that's why we have this batch size. You will see that when we try to train the network. Okay. And in order to make things work, we will be importing TensorFlow, STF. So in order to use batches, we need to create train dataset as a batch. Okay. This is basically, forget about this, just try to understand this is creating your batches from basically your training data. And if you take a look at the type of what you generated, that's a batch dataset from TensorFlow. Okay, so these were basically the preparation of the data. We converted the data into tensors here. We created our batch datasets that we will be using for the training. Now it's time to define the generator and the discriminator models. So in this function, we will basically define the generator model. Let's remember what it was doing. We will feed random noise to this generator, and it's gonna produce us a handwritten digit, which is 28 by 28. Okay. Now let's take a look at what we have as layers in our generator model. This is basically the definition. We will create a sequential model. At the very beginning of the layer, we have a dense layer that's composed of 7 by 7 times 256 neurons. So this is a dense layer because we will be feeding not an image, but just a one-dimensional random noise, which will be consisting of 100 values. So we will be converting this, okay, converting this value, 100 values, into 28 by 28 images. So why we have 7 times 7? Why didn't we just write the multiplication of these numbers? So here we are starting with 7 by 7 image-like structures. Okay, and then we will be reshaping them to a 7 by 7 tensor, and within each iteration we will upscale this 7 by 7 image to 14 by 14 image, and then we will upscale this 14 by 14 image into 28 by 28 image. Okay, so we will be starting with random noise, then we will be applying Bayes normalization and leaky ReLU to this random noise. This is still a dense layer, and then we will be reshaping this layer to a tensor which has a 7 by 7 width and height and 256 depth. Okay, and then with each operation, as you see, we are not using conv2d anymore. We are using conv2d transpose. That's an operation we have seen last week. That's to increase or upscale this tensor. Okay, and with each operation we will try to make this little image bigger and bigger. So let's try to understand the network, and then we will take a look at basically its visualization as well as the summary. For now, we created a tensor which is 7 by 7 times 256. Okay, and then we will apply a conv2d transpose, and we will decrease the depth of this tensor with a convolution filter of 5 by 5, and since we are using a stride of 1, we are gonna have 7 by 7 images at the end. It's not gonna upscale, because if you want to upscale things, you need to define strides as 2, as we do in the next layers. Okay, so we reshaped the tensor 7 by 7 that created a 3-dimensional tensor, and with this operation we just reduced the depth of this tensor, nothing else. And then we applied Bayes normalization, we applied leaky ReLU. Okay, in this operation where we will be decreasing the depth to 64, we are basically increasing the width and height of the image by 2. So from 7 by 7 images, we are gonna have 14 by 14 images. Okay, with this layer stack. And then we apply Bayes normalization as well as leaky ReLU. Now we have a 14 by 14 image, or 14 by 14 tensor with depth 64. We will be having another convolution 2D transpose which will be producing a depth 1 tensor with stride 2, which will be generating a 28 by 28 by 1 tensor. So this is an image. This is the image we are trying to get. So what we started is, we started with 100 random numbers. We fed them to our dense layer. We applied Bayes normalization, leaky ReLU. We converted this to a tensor, and then we basically upscaled them. Okay, with the convolutional neural networks, we were downscaling things. With conv2d, now we use conv2d transpose in order to upscale things. So we create a small image here, we create a larger image here, and then we created the full image here. Now let's see what this is gonna do. So we basically call the function to create the generator, and then we create a random noise with 100 numbers here, and then we basically call the generator to create us an image, and that's what we come up with. This is the image generated by our generator. So we were expecting a handwritten digit, and that's crap generated by our generator because it's not trained yet. It doesn't know what to generate. It's basically just using the randomly initialized architecture in order to create us this thing. Okay. Now let's try to visualize. Let's execute what we will have with that. That may take a little bit time. Now we will be using Visual Keras in order to visualize our network. See, it again generated something which doesn't look like anything but a digit. So we will be using Visual Keras, and generator is the model we would like to visualize. So this is how we visualize our generator. If you remember the convolutional neural networks, it was basically the other way around. The more crowded or the bigger layers were at the left side. Now we have the bigger layers at the right side. And let's take a look at the code as well as the figure. At the beginning, we have a dense layer, right? We have batch normalization here, and we have leaky ReLU, these three layers. Let's take a look at the code. We have a dense layer, we have batch normalization, we have leaky ReLU. Now we would like to see a tensor with width and height 7 and depth 256. Okay, when you take a look at the shape after leaky ReLU, now we have this guy. Okay, that's the reshaped layer. Now we started generating our image. This is the first thing. That's a 7x7 image. Okay, you can think this as a 7x7 image with depth of 256. Now after that, you see we have a conv2d transpose operation, which is reducing the depth from 256 to 128, but it's not changing the width and height. And we have yet another batch normalization and leaky ReLU here. Okay. And then you see we have stride 2 here with conv2d transpose. We are reducing the depth of the tensor to 64 and increasing the width and height to 14. You see, we increased the width and height of the tensor and we reduced the depth. And we have yet another batch normalization here, and we have yet another leaky ReLU here. And at the final layer, we have now a 64 depth, 14 by 14 image. Okay, what we need is a 28 by 28 image with depth 1. Therefore, we apply another conv2 transpose operation with stride 2. Therefore, this 14 by 14 image is upscaled to 28 by 28. And since we define our conv2 transpose operation with depth 1, now we have an image 28 by 28 and with depth 1. So that's the final layer of our generator. See, this is basically the reverse of a CNN. And when you use the summary command, the generator.summary, you basically will see all the layer definitions, how many parameters each layer have, how many neurons each layer have, the layer architecture. You basically see after the reshape we have a 7x7 times 256 tensor, then we convert this tensor to 128, and then we upscaled it, and at the very end we upscaled it to 28 by 28 by 1. So this is how we defined our generator model. Since the GAN needs to use a discriminator model as well, now we need to define a discriminator as well. That's slightly easier than the generator, basically. That's yet another sequential model. So we will be starting with a convolution operation. That's something like a CNN. It's gonna have depth of 64. It's going to get input shape of 28 by 28 by 1 tensor. So this is the basic shape of our handwritten images, and it's gonna have a stride of 2, which means it's going to reduce the dimension from 28 to 14, basically. Now we have again the leaky ReLU, and now we have another layer called the dropouts. And the functionality of dropout is basically it's removing some neurons from that layer, and it's gonna remove the 30% of the neurons in that layer. We usually use the dropout layer so that the network doesn't memorize. So for better generalization, you need to use dropout layer. Now that we have these definitions, we will have another convolution layer which will increase the depth from 64 to 128. It's still gonna use the stride of 2 in order to reduce the image dimension. We will have leak ReLU as well as dropout. Then we have a flattened layer, and then we have a dense layer with 1 neuron, because the discriminator just needs to say whether that's a true image or a false image. Okay, that's 0 and 1 output. If it is a real handwritten digit, then it's going to output a 1. If it is a forged handwritten image, that it's gonna output a 0. Okay. So let's initialize our discriminator and then try to visualize our discriminator with visual keras. As you see, we have the convolution layer and then leaky ReLU and then dropouts. We're not applying max pooling basically with this. We're just downscaling it by using the strides of the convolution. Okay, that's another way of doing that. So we have yet another convolution layer. We have leaky ReLU, we have dropouts, and then we are flattening it, and then we are adding a dense layer in order to make our decision. So this is how we visualize it. If you remember, the other network was basically the other way around. We are starting with some random numbers and then we are upscaling things. In this network, we are downscaling things as we go to the right. And when you take a look at the summary of the discriminator, you can basically see the shape of your network. Okay. Now comes the slightly more difficult part. We will be using binary cross entropy for the loss, and then we will be using 2 functions. One is called, or one we will be calling as the discriminator loss, and the other one we will be calling as the generator loss. And if you remember from the slides, the discriminator will be using real outputs as well as the fake outputs, because the discriminator's job is basically to discriminate whether something is fake or real. Okay, and then it's going to use the summation of real loss, I mean the loss coming from the real images and the loss from fake images, and the generator will just be using the loss, the cross entropy loss from fake images or the fake output. That's basically the difference between the discriminator and the generator training. In the discriminator training, we will be using real output and fake output, and for the generator, we will just be using the fake outputs. And we will be defining the optimizers for both discriminator as well as the generator. We will be using Adam optimizers. This, you don't need to know this. Basically, this is defining checkpoints. If you are training a big network, such as GANs, it's always a good idea to save your work at some checkpoints because if something happens, if your computer crashes, if the electricity is gone, you would like to have something in hand. It's always a good idea to use checkpoints. For now, just forget about it. We will be defining number of epochs. We will be defining the dimension of the noise we will be providing to the generator. And this is for illustration, just forget about it. We will be creating 16 images in each iteration for illustration purposes. This is for illustration, just forget about it. You don't need to understand that part. So this training step is an important function. We will be coming back to this. Let's take a look at the train function. We will be providing this or batch data set, and then we will be providing the number of epochs to this train. Okay, and basically for each epoch, it's gonna call the train step, the function above. We will take a look at that. So this is the most difficult part, the train step. We are providing the train step, the images. Okay. And then initially we create random noise for the generator. Okay. But this is not just single image. That's why it's called images. This is all the images in that batch. Remember, we have 256 images in one batch. And we are providing 256 images to this operation. And it's producing first noise and then feeding this noise to the generator so that the generator generates some images. This is the first operation, generating first images. Now we need to use the discriminator to see how it performs for the real images. Okay. We are first providing the real images that we provide to train step. So it's creating real output for the real images. And then we provide the generated images to the discriminator so that it provides us the fake output. Now we have the generated images for that iteration, for that epoch. We have discriminator's outputs for the provided images, and we have the discriminator outputs for the generated images. Now we need to calculate two losses. We need to calculate the generator loss, which will be just using the fake outputs, and we need to calculate the discriminator loss, which will be using the fake output as well as the loss output. Okay, now we have two losses, one for generator and one for discriminator. So this was it actually, and the rest of the operations are just using these losses in order to recalculate the gradients or in order to recalculate the weights and biases. So the difficult operation is here. You generate images, you provide the training images to the discriminator, you get real output, then you provide these generated images to the discriminator, you get the fake output, and then from this real output and fake output, you get the generator loss from the fake output, you get the discriminator loss from real output as well as the fake output. And you basically use these losses in order to recalculate the gradients, and from the gradients you basically recalculate the weights and biases, and in each iteration you get better and better results. So that's basically how you train your GANs. Since that's gonna take some time, I will be providing this example. You can use Google Colab in order to make the training yourself. I will be loading what I have trained beforehand for the generator. Oops, So that was not good. I just saved something that I shouldn't have saved. If I didn't do that, I could have used basically the generator to actually generate the image. And once you make the training, you can still generate noise and provide noise. And if you, for example, provide this noise to the generator after the training, as you see, we can come up with uh, these handwritten digits. So I gave it a random noise. It provided me something like a 9. Since I saved on top of my previously saved model, I'm not able to right now load that and make a demonstration with something else. But as you see, after the generation, after the training, the generator is able to basically create us an image that looks like a handwritten image. And in each iteration, let me show you the epoch output for each iteration. You see, this is the output from the first epoch. We provided it noise, and it provided us a 4x4 image that doesn't look like an handwritten digit. And in each iteration, as you see, it's starting to look like a handwritten digit. And if you go further and further, you see it's learning how to generate handwritten digits. And after all the iterations, as you see, once you provide the network random noise, it's basically providing you a handwritten digit. And that's how you basically train the GANs and use the generator in order to generate images.